Alright, we're back with the Units 4 through 6 opener for the Semester 1 exam review for chemistry. First of all, we're going to talk about Unit 4, electrons and atoms, and the first set of problems has to do with electron configurations. So we'll go over a few of those examples. Okay, so starting with the very first one, calcium, just kind of review over this. We definitely need a periodic table to write these, and that's definitely a system that we had learned for writing electron configurations. I asked you to write the longhand version. So we're going to look at calcium, and it's right here. This is the S block. Okay, so we have to get all the way up to calcium, filling in electrons until we've used up all 20 of calcium's electrons. So kind of write this while watching down here. Okay, so we always start in the first principal energy level, and this is the S block here that we're filling in to start with. Okay, so we have first principal energy 1s1, 1s2. 1 stands for the principal energy level, S stands for the orbital that we're filling in, and then 2 is the number of electrons, which is there's 1 and then 2 electrons that we're filling into that orbital. Okay, moving on, so we have to keep going until we get there. We're moving into the second row here. So 2s1, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s1, 3s2, 3p6, and then finally 4s2. So you see a pattern emerging here. S orbitals hold 2 electrons, P orbitals hold up to 6 if all 3 suborbitals can be filled. So kind of moving on here to copper, and the reason why I want to go over copper is because copper is an exception to the general electron configuration rule. So we'll do the shortcut for this one so it doesn't take too long. So to do a noble gas shortcut, find the element that you're trying to write out, which is in this case copper. Go up a level and move all the way to the right to figure out which noble gas comes before it. So the noble gas that comes before copper is argon. We have to put that in brackets. Then it's 4s1, 4s2. Now this is where we have an exception. So we go to the 3d orbitals, and basically normally we would go 1, 2, 3, 4, 5, 6, 7, 8, 9. But because copper is an exception, we only put 1 electron in the s orbital, and we move an electron up into the d orbital to fill them all the way up. So this is actually going to read 4s1, 3d10. Okay. When we're looking at an ion, we have to think about how many electrons we're adding on to the electron configuration for that ion. So for phosphorus ion, P3 minus, we're going to look at phosphorus down here. It's got 3 extra electrons than the atom for phosphorus does. So it has an electron configuration that's similar to argon. So it's got 1, 2, 3 extra electrons. It's like argon. So I'm just going to write argon for now, and you can fill out the longhand one to get more practice, but that gives you the idea of how we do the electron configuration for an ion. You can find the rest of these answers, put up the answer key as a document that you can check. Alright, moving on. So another type of problem that we encountered in Chapter 5, Unit 4, had to do with looking at the frequency and wavelength of light and its relationship to the speed of light. So we're going to take a look at this problem. Your favorite radio station emits electromagnetic radiation at a frequency of 103.5 megahertz. What is the wavelength of this frequency in meters? If you're listening out there, what is this radio station as well? It's kind of fun. But what we need to know to start is this equation. That's really the starting point for this problem, is knowing that all these things, the frequency, the wavelength, they're related, and they're inversely related, and they are equal to, when you multiply them together, to the speed of light. So speed of light, which is 3 times 10 to the 8th meters per second. Okay, so we know what the frequency is. It's 103.5 megahertz. But we don't know what the wavelength is. There's one problem, and that is we need to convert the frequency into hertz, because in order to plug into this equation, hertz is 1/seconds, and we can't use megahertz. We have to get into normal hertz. So we're going to have to do a dimensional analysis problem. So this is our starting point. We're trying to get into hertz. So we're going to use this conversion factor that's given in the problem to do so. So before we can plug into that equation, let's go ahead and convert into hertz. So 1 megahertz, we got to cancel out megahertz. So we take the 1 and megahertz, put it on bottom, and then we have 1 times 10 to the 6th hertz on top. Okay, so we'll plug into our calculator. You want to use the second E button for that exponent. So that would look something like this. You go 103.5 times 1e6. Okay, and then you get like a really big number. So we can write that in scientific notation. We're going to count how many times we have to move the decimal point over. 1, 2, 3, 4, 5, 6, 7. It's 1.035 times 10 to the 8th hertz. Okay. So next step is we're going to plug into C equals lambda V. So C equals lambda V, we're solving for wavelength. So let's get wavelength isolated. We're going to divide both sides by V. So wavelength is going to be equal to C divided by V. We're bringing this guy over to the other side. So C over V. Okay, so wavelength equals 3 times 10 to the 8th meters per second over our new value for hertz, okay, be really careful plugging this into your calculator. You're going to want to use parentheses to start, so 3e8, put that in parentheses, 1.035 e8. And you get 2.89 or 2.9 meters. Okay, so that's the wavelength of KISS FM is 2.9 meters. Okay, moving on. So after electrons and atoms, we talked about periodic trends and the periodic table. So you do need to know how to label the periodic table, where the metals, nonmetals, and metalloids are, and the staircase, how that divides everything up, transition metals, so on. This is one particular concept in that unit that was that we're going to look at, and that is periodic trends. So one of the trends that we looked at was atomic radius. Now, the trend for atomic radius, if we wanted to kind of sketch out our own version of the periodic table, just to talk about that trend, kind of rough sketch of our periodic table, you know, got their transition metals, halogens, noble gases, inner transition metals on the bottom. The trend says that the biggest element is down here. Cesium is the biggest element. It's down and to the left. We have the atomic radius trend goes up as you go down and to the left. So if you break that down, going down a group, the size of the atoms increase, and then going across a period this way, the atoms increase in size. So we want to put these in order of decreasing atomic radius. We want to put them in order of high to low. So we want to start with the highest and then go to low. Okay, so keep that in mind. We want to go from the highest atomic radius to the lowest. So we're looking at phosphorus, arsenic, and sulfur. Okay, and they're all by each other on the periodic table. So this way is the biggest atomic radius, is going down and to the left. So first we want to look at which one is lowest and to the left. Well, arsenic is lowest and it's furthest down to the left. So this is actually going to be the biggest atomic radius. So we're going to start with this guy. This guy is going to be bigger than both of these. So it's the biggest. The next one is going to be the one that's further between phosphorus and sulfur. These both are in the same period. So phosphorus is further to the left, which means it's closer to the bottom and left of the periodic table. So the next is phosphorus, and then after that is sulfur. Okay, so that's how you approach one of those problems. And kind of a similar type of problem, but you got to be careful, we're going the opposite direction here, is electronegativity, increasing electronegativity. So we want to go from low to high electronegativity, trying to get increasing order here of these three elements. So remember, electronegativity is the opposite trend as you go up and to the right on the periodic table. It increases in value. We do not assign a value for electronegativity to the noble gases because they do not have any want or need to attract any more electrons. They have a filled octet. They are happy as could be, and they don't pull on electrons when they are in a compound. Okay, so yes, the trend is the opposite. Fluorine being the highest electronegativity, so it kind of ends there. Electronegativity increases as it goes up and to the right. So we could break this down as you go across a period. I'm going to ink here. As you go across a period that way to the right, electronegativity increases. As you go up a period, up a group, sorry, electronegativity increases. So it's the opposite on the periodic table. So we want to go increasing. We want to start with the lowest. So the lowest one will be furthest to the left and lowest in its group. So we're going to find these three elements, and they are right by each other. Okay, so the lowest to the left is tellurium, so we'll start that. Okay, this one is smaller in electronegativity value than selenium, which is further up. And then the one that's furthest to the right and highest is bromine. So these go in increasing order. So bromine being the highest electronegativity. So the most difficult part of these problems is make sure you don't mix up the decreasing and increasing order, and that you get the trends going in the right direction. Okay, so continuing onward. Naming. So you do need to know how to name molecular and ionic compounds. So I might give you a mixed batch, just like I'm doing here, naming and bonding. So we have to look at, first of all, is this a molecular